I'm going to talk about exoplanets. You know our planetary system. This is not on scale, but it shows the 8 recognized and well-known planets of our system. And the title I gave is De Natura Rerum, and exoplanets and exo-Earth. And of course, this topic was already addressed 10 years ago, exactly, which was exactly 10 years after the discovery of the first exoplanet in 1995. I will not repeat the paper I gave, which is in the proceedings of the session Path of Discovery 10 years ago, because there has been so much in between that I will barely be able to cover that. At that time, only 133 exoplanets were known, and the first image ever obtained of an exoplanet was not even confirmed. It has been confirmed since. You see there a star, which is a brown dwarf, a very small and not very bright star, and the planet in red has a mass between 5 and 8 Jupiter mass. It's 50 AUs from the star, so it's about the distance to Neptune, and it's a young system, 5 million years, compared to our system, which is 100 million, which is 1,000 times older. And the discoverer of this very first image is Anne-Marie Lagrange from Grenoble in France. Today, in our galaxy, statistics begin to indicate that in the average, every star you see in the sky has a planet. This means about 100 billions of exoplanets, and 2,000 about, I'll come back to this, are now identified and more or less characterized. Now, how does this concept of exoplanet relate with the evolving concepts of nature? The title of our session. In my previous paper, I recall the long history of a quest which began metaphysically with Democritus, was disputed theologically during the Middle Age, provided fantasy to poets and writers, and emerged as a scientific question during the 19th century. We remember that along this path, Giordano Bruno expressed ideas very close to the Lucrece views, was condemned to the fire, and I think he should at some point be rehabilitated, even if there were other reasons for his condemnation than only exoplanets. And finally, in 1995 came the discovery of the first exoplanet by Mayor and Kellos from Observatory of Geneva, observed in the French Observatoire Saint-Michel de Haute-Provence in southern France. This planet was very strange. It was about as massive as Jupiter, but it was extremely close to the star, much closer than Mercury is to the Sun, and it was a puzzle, which is today solved. Well, if I recall Lucretius in De Natura Rerum, he was transmitting the ideas of Epicure to Roman people, and he writes, "By no means can it be thought probable, when infinite space is open in every quarter, that this one globe of the earth and this one heaven have been alone produced, especially when this world was made by merely natural causes and no purpose. For this reason, it is irresistibly incumbent on you to admit that there are other combinations of matter in other places, such as in this world, which the ether holds in its vast embrace. There is no finalism, no specific purpose in Lucretius. Nature for him is only a convenient word, a concession to his Roman public, not a deity, neither a metaphysical entity. Only random motion and matter create the world as experienced by humans. Does it therefore, and that's the modern question we deal with, belong to the nature of things to produce habitable planets and eventually life, just as it is in the nature of quarks to produce the atomic elements, themselves producing the millions of molecules. In this short talk, it will be impossible to render justice to the vast amount of observations and publications in this exploding field of research. This was well summarized last year in a dedicated issue of Science, which I recommend the reading to go deeper. Excellent papers there. And those trends will try to show you that we have to define a new and less anthropocentric concept of a planet. So those last 10 years have been 10 years of discovery. And of course, the first question to answer is, what is a planet? 20 years ago, with the only example of only one planetary system, ours, defining an exoplanet was inevitably heliocentric, if not anthropocentric, including a preconception of what such an object would be. And we all remember the International Astronomical Union definition of our own system, because it led to the exile of Pluto from the list of the 9 planets, coming then to 8 planets. A planet is a celestial body that is in orbit around the sun, has sufficient mass for its self-gravity to overcome rigid body forces, so that it assumes a hydrostatic equilibrium, which means nearly round shape, and has cleared the neighborhood around its orbit. But with the wealth of new discoveries, the definition for an exoplanet has to take a much broader and more empirical view. And I give you here 2 tables. The first one is an attempt, a recent attempt to denominate the various cases of simple exoplanets. Some are Jupiter-like, they are gaseous giants. Some are hot Jupiter. They are similar to Jupiter, but they orbit very close to the parent star, closer than Mercury. So they have migrated to this point, and it's a very large fraction of the confirmed planets, almost half of them. This is not because they are half of the existing population, it's just because they are easier to detect. So this is an observational bias. At this category, the first planet discovered by Mayer belongs. Then we have the hot Neptunes. Neptune's mass is 17 times the mass of the Earth, and hot Neptunes are between 10 and 50 Earth's mass. We have the mini Neptunes, which are only 10 times the Earth's mass. We have the super Earths, which are between 2 and 10 Earth's mass. And finally, the Earth's mass planet, which are about 1 Earth's mass, and what we call specifically exo-Earth, which would be not only an Earth's mass planet, but it would also be in what's called the habitable zone, which I will describe later. The second table gives more complex cases of exoplanets, like a planet around a pulsar, which actually was unexpectedly discovered in 1992, which is a very strange case, which has not repeated in many other instances. Rogue planet, it's a planet floating in the space, having lost its star, or the star has lost its planet, and there are probably many of them. Ocean planet, it's a planet which is covered by an ocean, either of melted rocks if it's close to the star, or liquid water if it's further away. Circumbinary planet, a planet orbiting not only 1 but 2 stars. There is one case known today, very well known. There might be even circumtertiary planets, and many stars are double or triple. Eccentric planet, this is a planet with a very high eccentricity of the orbit, which modulates the temperature at a high degree, and so on and so forth. And finally, in the list, there is also exomoon. No moon of a planet has been discovered yet, but we should expect that to come soon. Now, those cases make difficult the definition of an exoplanet. And this is an attempt that IAU is proposing and which will certainly change in the coming years. The mass limit is below the thermonuclear fusion of deuterium. This is about 13 Jupiter masses. It has to orbit a star or stellar remnant. This is for the pulsar. And no matter how they are formed, which means that the capture of a planet by a star coming from another star, this is still the planet of the star. And the mass-size relation we use at the moment is the same as in our solar system, pending more information. And there are also substellar objects, which are called brown dwarfs, which are not stars, which are not planets. So you see the definition is open for evolution, and 10 years from now, it will certainly be different. Now, since 2004, so in the last decade, essentially ground-based and space observatories have been discovering planets, and here is the result. You see the rate of discovery, the counts are in ordinates, and the year is in abscissa. We have the first in 1995, and you see the tremendous increase. And when I did this graph last night, there was 18 and 32 cumulated count of planets. But there are also a long list, nearly 4,000 planets, which are awaiting a confirmation of detection. So the rate increase, and one aspect of this increase is the last bin that you see so high, which is due to the Kepler NASA observatory. So the bulk of those discoveries came from two methods. There are many methods, but two main ones. The first one is the Doppler shift of the velocity of the star. So it's an indirect detection. This is the way 51 Pegasus was discovered. And many of the planets are either discovered this way or confirmed by this method. The other method is transit. When the orbital plane is seen edge-on from the Earth, then at each revolution, the planet passes in front and then in the back, and that dims the light of the star by a little bit being 10⁻⁴ or something like that. The smaller the planet, of course, the dimming is. And this photometry can be very accurate. It can detect planets as massive as 10⁻⁴ times the mass of the Earth because of the quality of the photometry. Now, from this measurement methods, one can derive the main physical properties of an exoplanet, the mass, the radius, the density, and also the orbital characteristics, the period, of course, but the eccentricity and the number of planets in the system around the star. Now, obtaining a direct image, as the one I showed, of an exoplanet is very difficult because of the contrast in brightness between the star and the planet, which is very close to it. This contrast can be as high as 1 billion. So despite of this, with coronagraphic techniques, several tenths of planets have been imaged today. They have masses comparable to Jupiter because being big, of course, they are bright and more easily discriminated from the star. And the quest for lower mass planet in order to approach the mass of the Earth has some symbolic importance. Some people say this is the holy grail of exoplanet research, and this is very active. The first exoplanet, which has almost exactly the mass of the Earth, Gliese 511e, was observed in 2009, so it's fairly recent. Now, from this large amount of discovery, I will just try to pull out some outstanding results. There are many references. I mentioned just a few of them because there are websites where everything is kept up to date, day by day, essentially. And there is also this paper in Science. Many aspects which I will only extract a few of them, the more salient facts. Now, parent stars. Which stars do have one or several planets? Now, the search began with stars like the Sun. It was natural to do that. But now we know that planets exist around almost all types of stars, from hot stars, short-lived, the A stars, to cold and long-lived ones, the M stars, and even around binary stars, as I said. M stars, cold stars, are very interesting because their stars are extremely abundant in the galaxy, as in any galaxy. They have a low surface temperature, less than 4,000 degrees compared to 6,000 for the sun, which means negligible ultraviolet emission. Temperature is favorable to molecular composition complex of the atmosphere. And their lifetime is long, billions of years, which is favorable compared to short-lived stars as a star, for instance. Now, enough cases today are observed to begin sound estimates of the average occurrence of exoplanets in our galaxy. And I already mentioned this incredible result that on the average, there is one exoplanet per star, since many stars will have 3, maybe up to 10, maybe more exoplanets, then it means that not every star we see in the night sky has a planet. This is just a statistical average. Now, stars and planets form from an interstellar cloud collapsing through a gravitational accretional process, and we know that quite well now. And for the star formation. But the formation of the planetary system is much more complex. Here is the image of such a disk around the star Fomalhaut b. The star is hidden with the disk, of course, and you see this ring of matter, which is small grains of dust which scatter light and emit infrared, and near the ring you can see a planet which has been followed from 2004 to 2012. It's more or less a Jupiter mass-like planet, and the distance of this object from the Earth is very close. It's only 25 light years, so it makes the study, of course, easier. This is another view of this disk at millimetric wavelengths taken from the Chile Atacama Observatory of Europe, US, and Japan. And you can see this, the picture was not completed. It's a long process, and so only half of the disk at that time was mapped with this millimetric emission of grains of dust, which give hints on their chemical composition. And if one tries to make a schematic of the planetary formation, it's very complicated. And this is why the statistics of this formation process is not well assessed at all. I mean, given a star forming, given a disk with a known amount of mass and a known composition around the star, can one predict how this disk will form planet, how many, how big the mass they will be, etc.? Will they have an atmosphere? All those questions we want to know about. And you see this is a very intricate, coupled, nonlinear physical description. Also, the physics is not, all the physics is known of that, but it's just very complex. The conclusion today is that, but that's solid, that the formation of an exoplanet is a stochastic process with many, many parameters entering into this picture. Second question, planetary orbits. Do planets have circular or elliptical orbits? Of course, we are biased at the beginning because in our solar system, most of the orbits of planets, I don't speak of comets, are nearly circular, very low eccentricity. And the orbit determines the stability of the temperature of the planet. If the Earth had a very elliptical orbit, then of course the changes of temperature on surface would be terrible. In fact, many orbits show high eccentricity, which implies those changes of temperature, which, if the planet has an atmosphere, also implies strong winds, strong exchange of matter, of dust on the surface, etc. Here is a graph with the discovered planets and their position on the semi-major axis and the eccentricity. So the Earth, of course, is the red point there with very low eccentricity and an axis of 1 astronomical unit. So you see many planets are to the left of this red point, which means they are much closer to their star than the Earth, up to 10⁻², AUs, and eccentricity can be as high as 1. Very, very elongated ellipse. In giant gaseous planets, the hot Jupiter, are very close to their star, which means surface temperature beyond 1,000 K. They have not been formed at this point. They have migrated, and there was one problem which was pointed out after the first discovery. How could such a big planet be so close to its star? They have migrated, having been formed far, far away, where matter was available in the disk, and then migrating toward the star due to viscous friction in the disk. Another question, density. Can one distinguish between rocky, telluric type planets from gaseous planets? The density of a planet is rather easily measured because when one has a transit, then the amount of dimming of the starlight immediately gives the diameter of the planet. And if the mass is derived from the orbital parameters, then one gets immediately the density. And this shows you how a large number of planets distribute in this diagram. The units are Earth's mass and mass radius. And you see that it's not very visible, but some points are the planet of the solar system there. And you see that there are many planets which are close to the density of water, of rocks, even of iron, and others are density of hydrogen. And there are cases in between, which indicates that some of those planets they are massive enough to keep a hydrogen envelope, but not as massive as Jupiter. But there are puzzling cases. For instance, a recent discovery by Kepler, the planet KOI 314c, it's at a distance of 200 light years. It has the mass of the Earth, but it is 60% larger. So it is less dense than the Earth, and this is probably due to a very thick atmosphere of hydrogen. But this is problematic again because the gravitational field of the Earth, as you know, is not sufficient has not been conserving the hydrogen. Other question, the masses of the planets. What do we know about the mass distribution? And it turns out to be essentially bimodal. We have the Jupiters and we have the Earth. And this has to be confirmed, of course, with less biased observation. But the interesting thing is that objects like Neptune, which is 17 times the mass of the Earth, are very common, actually as common as the low mass object. Do planets have atmospheres, and of which kind? The composition of atmosphere can be measured. This is a very important point. Even if one does not see the planet as an individual point, the transit gives two occasions to measure the atmosphere. When it passes in front, then the light of the star goes through the atmosphere of the planet, the green circle there, and modifies the spectrum which is observed. And when it goes through the back, then it's fully heated by the star, and then suddenly this infrared emission disappears, and so one can, by subtraction, derive what it is. The result is this. This is an example. Most of those atmospheres contain water because it's abundant, CH4, CO, and CO2, and methane. And model in orange on this picture with water and methane fits very well the spectrum. And also it's consistent with the abundance of the elements that we know. Habitable zone. This is a concept which has been progressively developed, initially in a very simple idea that if you are away from the star, there is a certain distance range where the water can be liquid. If you are too far away, it's ice. Too close, it's vapor. But this depends on the greenhouse effect, of course. Like Venus has a very strong greenhouse effect, and water is completely evaporated there. On the other hand, Mars has no greenhouse effect, and water is icy for the little we know, present. The Earth has exactly the good greenhouse effect to raise slightly the temperature above 0 degrees. So we cannot, if we define the habitable zone as the region where the liquid water could exist, this cannot be uniquely defined without also defining the atmosphere. So from that, one can search planets being close or in this habitable zone. And there are already a few planets close to the mass of the Earth which have been found in this habitable zone. Now, I like to show you this because this is an event which will happen 2 weeks from now. The landing on the nucleus of the comet 67P Churyumov-Gerasimenko, 1 billion kilometers away from the Earth. This lander is going to scrub the ground and has about 10 instruments on board and will analyze everything. And then it will transmit the data to the Earth. Now, about the question of life, one has to be very careful when landing on a body because one can pollute the body. And the motto of the people who prepare those instruments could be the ones written in a nearby rune. Trovare pulito è un piacere, lasciare pulito è un dovere. And this is very difficult because the surface of the moon has been indeed polluted by Apollo's missions. So I will not extend my talk to the search of life because I would only repeat what has been said at the week that Father Funes and the Vatican Observatory organized with this academy in 2009 and which has published very nice summary conclusions which are available on the website. The conclusion there was our ignorance, of course, but also the extraordinary ability of the life on Earth to adapt to the most extreme environment, and including places like in the hydrothermal vents, which do not involve starlight. So if one thinks of the extreme diversity of exoplanets already found, the conditions, both chemical, physical, and radiative, on those places are such that they at least offer space for experimentation and speculation. The problem is difficult, and the main difficulty, beside making models, chemical models of life, and of course exploring what we heard beautifully on proto-ribosome and so on the Earth, the main difficulty is to decide which unambiguous biosignature could be available. Take the Earth. You know, life is on the Earth. Now we look at the Earth from a distance, say from Jupiter or even beyond that. And what do we see? We see a spectrum, and this, we don't have an image. If we had an image, we could see the continents, the cloud, the vegetation, and so on. But as long as we don't have an image, and it will take probably several decades before we have an image of an exoplanet surface, even the closest ones, then we see spectral lines. And we have to be sure that any of those lines which we identify as biosignature is expressing a state of strong non-equilibrium. Now, for the Earth, the state of non-equilibrium, sign of life, is the presence of oxygen, which has no spectral line available easily, but makes ozone. And so the ozone little dip there is the only signature of life presence on the Earth. The signature of chlorophyll is much more difficult to obtain. So the problem will be difficult, but it's not unsolvable. So you see that in the last 10 years, this field of exoplanetary research has exploded. The observing tools have been refined, and a new generation of instruments has been prepared with higher sensitivity, a better adaptation to the question. So we can expect a lot from the next decades to come. One should keep in mind that the complexity of the planetary formation gives rise to this extreme diversity of cases, of masses, of atmospheres, of composition, and so on. This diversity is produced by a kind of niche where both gravitational forces and physical and chemical reaction due to electromagnetic forces play together. This is not the case in a star where gravitation is dominating, and it's not the case in our laboratory where electromagnetic forces are dominating. But the planetary formation scheme is just where both play together. This is also interesting. So for stars, we have a very simple Hertzsprung-Russell diagram, which in fact with mass and luminosity or color, you can define a star. It's not expected to have the same easy classification for exoplanets. So my conclusion is that cosmology of the early universe allows to explore the transition from a universe entirely ruled by quantum fields to one everywhere dominated by matter of atoms. The chemistry in the interstellar medium reveals the transition from atoms to molecules everywhere. Exoplanet research is now offering the field of investigation for the transition from molecules to life. Pierre de Chardin was describing a universe of increasing and converging complexity with successive emergence of matter, life, and spirit. Astronomy has unveiled the first emergence and is on its way to unveil the second emergence. Thank you.